I like to apply what we call the 3 B's of resource planning: bust, bug, and brilliant. So it could be bust in the input. Maybe we had not defined properly the input assumptions in the model. Or we could have some bug in the model, where somebody just mentioned this morning about the infeasibility, and I will be mentioning in one of my applied cases about the infeasibility. So there could be some infeasibility in the model. And the third one, which is the most interesting one to me actually, is the model is being too brilliant, meaning the model has revealed something about the system that we haven't thought of. The model had discovered something that we did not even anticipate. And now with this, again, with this combination, using the API and AI, we don't really treat the model like a black box anymore. We can have this deep understanding of what the model does and how the model processes its transaction behind the scene, how the actually optimization would happen behind the scene of the model. So right now, as we have access and control over the model, the question remains, what problems we're actually solving for? What do we care about? So in today's world, we have several components that actually impact the overall system behavior. And they're all interconnected. They don't move, they don't move in a separate direction. They're all interconnected, and they all actually impact each other. And as we can tell, renewable generation is growing so fast. We also can see significant growth in large demand centers that is also driving load and peak dynamics. So as we get the access of the API in the middle of this cycle, we can get all these dots well connected. We can actually understand the full picture of the plan. We can understand how these small components are impacting each other and how they're adding a value for the overall system behavior. So with the PLEXOS API, I call it as a game changer because it helped me see all the bigger picture, and it helped me connect all the small dots together across the energy system. And for a very long time, in our industry, our planning used to be driven by a single objective. What is the lowest cost possible, right? Like we used to care so much about what is the lowest cost that we can identify in our plan. However, in today's world, every decision we make is actually driven by 4 key priorities: reliability, sustainability, affordability, and regulatory. So we're trying to identify a plan that is energy reliable, economically reasonable, regulatory compliant, and also resilient. And as we actually employ advanced modeling techniques, API and AI and stochastic analysis, we actually can compare many portfolios across different scenarios to identify the best balanced plan, not just the lowest cost plan. So we're trying really to balance 4 key priorities here. And we're trying to identify the plan that gives us a well-balanced decision across all these competing priorities. And as we care about many things, right? As I just said, we don't just care about the economics and the cost. Since we care about many things in the plan, that would mean that we're going to actually produce many plausible futures. So we could have high load growth or low natural gas. Policy changes could impact our scenarios. High renewables, as I just mentioned, and sometimes extreme weather events, as everybody has seen before. And now, actually, the value of modeling isn't just producing more outputs. It's actually turning thousands of outputs into signals. And that actually would include, comparing scenarios, revealing patterns, identifying risk and the trade-offs. And that's where actually, again, the AI becomes really helpful because we're trying to compare many scenarios. We're trying to see how they're actually competing with each other because we're trying to balance the trade-offs. And that's, again, why where the complexity of decision-making is coming from. So because sometimes we may have a portfolio that looks great on cost, but has a reliability risk. Or we may have another portfolio that actually looks good in reliability, but it's too expensive. So we're trying to identify a plan that is informed, balanced, defensible, and actionable. And that's what I believe actually advanced energy modeling could turn complex scenarios into clear decisions. And that's we are trying to basically employ and implement these tools to get down to this final image down here. So everything I talked about so far about API, automation, and AI analytics, I believe would actually change the way we interact with the PLEXOS. I believe now we will have a better understanding of a PLEXOS, not just running simulations. We will actually analyze the uncertainties around the model better. And basically the AI will play here as the bridge. The AI will not replace the model. The AI will play here as the bridge to bridge the gap between the model complexity and decision clarity. And what I told you about today is actually part of the story. This is not all of the story. And what AI will do tomorrow is something could be different from what it can do today. But if we can understand what the AI is doing today, we can understand what the AI is capable of doing tomorrow. So I would encourage you guys to stay curious and to stay open-minded about applying many of these advanced energy modeling techniques and how we can leverage AI to help with that. So right now, I would like to show you 3 real-world applications that we have actually developed at American Electric Power using this unique combination between PLEXOS API and AI-driven analytics. So the first applied case, we actually we're producing a capacity expansion model. I guess you've heard about the capacity expansion model earlier in the presentations today. And with this capacity expansion model, we actually converted a lot of data that came out of the model into some clear dashboard. So this clear dashboard that you see here at the top is basically a conclusion of the plan that we landed with our RPS target. So with our renewable portfolio standard resource adequacy, we were actually trying to plan toward the goal that is basically asked by our regulators to be fully renewable by 2045. But we did not know what the preferred plan should look like. We had to run multiple plans. The plan I show you right here is only the preferred plan. But behind the scene of that, we had many data to process and many plans to compare against. So with this preferred plan, we were able actually to notice that we're investing in about 3 gigawatt of renewable resources for the next few years, especially at the beginning of our plan. And we're also actually adding some large CC and CT, about 3.7 gigawatts supporting drive resource adequacy and above requirement after 2033. So now we can see the full story, actually. We can see how are we doing against that target that we're asked to achieve, and how are we doing in terms of our reserve margin. As we look toward the future for the next 15 years, we can tell that only in 2032 we're a little bit below the reserve margin, below the reliability cushion that we have to achieve. And we can see in some other years that we're actually way above. So right now with this dashboard, we can truly see the full story and better understand what the model is actually telling us and be able to communicate those results with our stakeholders really easily. So the other applied case that I would like to mention right now is we were actually planning a study for one of our operating companies that they were actually investing in dual fuel capable. But the main challenge was in the first few years, the firm gas would not be available, and the system has to rely only on oil. So we had an oil tank available on site, and we had to plan with these basically unique constraints in the model. And also we had to run this stochastically with 500 scenarios across winter and summer for emergency events, range from very extreme to less extreme. And finally, we did land to our insight. But before I tell you about the insight, I want to tell you a little bit about the value of the tools we have implemented in this study, basically. So we had a lot of data we had to process. We were actually doing a production cost model for hourly detailed study for 3 years, hourly. And then as we did that for 500 samples, now you can actually, you can assume or you can imagine how big this data is. And we did not know whether this system is reliable enough or not, or this system may be reliable but has a higher risk. There was so many questions we're actually being asked to answer, but it would have been so hard to land to those answers without actually using some advanced technologies like the one we had right here. So toward the end of the study, we were actually able to summarize all the data that came from PLEXOS into this clear dashboard. As you can see right here, as we dispatch during emergency events, oil will go down. As you can see, the orange will go down. And then we had to rely on some oil tankers actually to come in and refill the oil tank on site. So we're also incorporating that into the dashboard. As you can see, the dark blue color is showing the refill events. And then you can see this orange line that is basically sitting on top of all blue and dark blue and light blue lines, where it means oil tank is reliable. And this is not only one case. That's why you see like many small lines connected with each other. This is not just one small case. This was the entire system for a production cost model for 3 years hourly. And we were able to tell our stakeholders right away that, look, this is the story of your system, given the fact you don't have firm gas for the first 3 years, and you're going to be relying only on oil, and with the refilling oil that would come along. So we were able to tell them right away how things would look like for the next 3 years of the plant system. And basically, we had this detailed table down here that shows them the real transactions that PLEXOS was optimizing. So that applied case number 2. With the applied case number 3, and that is actually the most interesting one, is typically we do find infeasibility in the model. That is the bug I was mentioning earlier. So bug in the model could indicate that we have some infeasibility in the model. But the challenge always is, where is that infeasibility is coming from? Or sometimes actually the infeasibility is quite healthy. It could be a good infeasibility, but we cannot tell whether it's a good or bad infeasibility unless we actually pinpoint the reason of the infeasibility, the root causes of the infeasibility. So we actually also developed, using the AI and API-driven analytics, we have developed a solution that can actually identify the infeasibility. And it was just like this. We had 15 million PLEXOS optimized transactions, 15 million. Out of that 15 million optimized transactions, only 800 of them were infeasible. We did not know how many they were. I got to find this number through this combination of API and AI. But actually, we had only 800. So you can imagine only less than 1%. Sometimes even people might ignore that less than 1% infeasibility. But that less than 1% infeasibility was so crucial to the system. And actually, we were able to identify the root cause of that infeasibility and tell where it is actually coming from. So using the AI and the API engine was such a game changer to come up with this solution that actually can identify the infeasibility and tell where it actually is coming from. So with that, as I said, with this 3 main cases and with the concept of API and AI, I would like to thank you guys so much for attending and for listening to my conversation. And I would encourage you to stay curious, to stay open-minded about what the AI is going to offer for the future, because what I told you about today is part of the story, and what is happening is even more. So thank you guys so much.